All right. So, yep, I forgot to record this session actually. So let me just again, start recording, and probably I'll take again couple of minutes to revise what we have discussed. So, hello guys, my name is Ravi, and today I'm going to take CCNP, Enterprise, and this is what we have agenda on the screen. The agenda is going to be the introduction, what all we have, and then we will follow. We'll go to the routing flow and then the EIGRP protocol, right? So when it comes to the introduction, as I mentioned, we have. I mean, I can divide this the whole CCNP program into five categories where you would have one routing, the second would have you would have the switching, third you would have the IP services, fourth you would have uh, layer 2 and layer 3 security, and then you will have the SD access and automation and programmability. That's what we have basically in CCNP Enterprise. Yep. So now talking about the routing flow, as as I discussed, what is routing is a process of sending packet from one host to another host through the layer 3 device where the route lookup happens. That becomes a routing. There are two types of routing: IP routed and IP routing. IP routed is something fixed every time. Either it would be IPv4 or it would be IPv6. Means either the data would be transported using IPv4 address, or the data would be transported using IPv6 address. That completely depends on what you use in your environment, right? The second is IP routing. Now IP routing is a process of selecting the best path, right, as well as learning out the destination. What does that mean? The IP routing is a process of learning the destination, means where the destination is, and to reach that destination, if we have multiple paths, what path, which path would be the best? That all happens in the IP routing. So I can say this way, uh, what all protocols that we use basically here. Yeah, for example, we use EIGRP or OSPF or BGP or ISIS. Right? These are the kind of protocols. I mean, RIP as well. Yeah, let's not forget this, though it's not there in implementation much, but still. So these are the protocols, and these protocols, what they do, they learn the destination, how to reach, and they have multiple paths. They would select one of the path as in the best path, you know, for forwarding the traffic, forwarding the data. That's what it is, IP routing, right? Now, IP routing is something. There are basically two types of IP routing again. So let me just do this one and two. So the first type of IP routing is static, or you can say default. Now this might overlap, yep. And the other one is dynamic, dynamic IP routing, right? So there are two types of routing: static or default or dynamic. What is basically static? Yeah, static is something where you are logging to the router individually and making entry of each network in router to forward the traffic. That's again very basic level, guys. Not gonna spend much time. Hope this much would be enough for you guys, right? And the default is pretty much similar. Again, you have to make manual entries for the default network when you have the existing or when we have basically one exit point to reach the destination, or maybe you want to send all the traffic towards one interface. We use default anyways. We're going to discuss separately. And then we have the dynamic. Dynamic is something, you know, here you have to enable the protocols in the router. Here you have to configure the protocols in the router. Router would learn all the prefixes, what all prefixes. Just remember, router knows all directly connected network because you're going to configure those, IP addresses, network on the interfaces. So router knows that, okay, these are connected interfaces, isn't it? What we are going to learn here, or what router is going to learn, is what it doesn't know, as in which all network indirectly connected, which all network that is not connected to the router directly, but it is still there somewhere in the network, right? So these routing protocols going to learn those prefixes and going to advertise from one router to another router. We would have more discussion on into it, right? And then finally, this dynamic has been divided into two: IGP and EGP. Hold on. Yeah. So later, the dynamic, we have IGP and EGP, right? So everyone knows about it. Interior gateway protocol and exterior gateway protocol. So IGP is something what? This basically is run within the autonomous system, within a domain, to exchange the, prefixes, network from one router to another router. So IGP happens basically, that advertisement happens basically within that autonomous system. Now, what is autonomous system? It's basically a number. Yeah. Let me just put it here. What is? It's nothing but uh, it's number between uh, between 0 to 64,556, I guess, or maybe 64 or 56. Yeah, that's AS is number between 0 to 64,536, basically, I guess. And this represents a domain. So one AS number represents a domain. There would be, private AS number, public AS number. That's something again we'll discuss. You guys can also, browse it. What is AS number? You will have a lot of explanation about it. What is the private range of the AS number? What is the public range of the AS number, and all that. Zero is not used. Last one, 65,536, I guess. That's what. Okay. By the way, just check this one. What is the last? I guess it is 65,536 or 64536, maybe. Yeah. Right. So IGP is run within the AS number, autonomous system number. EGP we use to advertise the prefixes between two AS numbers, right? Between two AS numbers. What does that mean? For example, let's say this is one AS number and this is another AS number. And here I have, the routers, right? So now these routers would exchange the prefixes, right? Using the IGP protocol, using the IGP protocol. Here as well, we have routers inside. Here as well, we are going to use IGP, right? But when it comes the advertisement between this AS number, let's say, for example, this is 100 AS and this is 2. So now just to exchange the prefixes between this AS number and this AS number, what we need is EGP, and EGP is now BGP protocol, right? So BGP makes, BGP is used basically for advertisement between two AS numbers. So IGP is within AS number, EGP or the BGP is for the in between the AS number, two different AS number. Yep. Okay, hold on. Someone asked question, I guess. You guys can ask over here. Yeah, I mean 65535. That's the correct. Okay. So now coming to the IGP, there are three different flavors of IGP. Yeah, there are three different flavors of IGP. When we say three different flavors of IGP, we have distance vector, not going to write everything, distance vector and link state and hybrid. Right? These are the three different flavors. When we say flavors, is it the actual protocol? Is it the protocol? No. This basically, shows how the advertisement happens, right? When we say how the advertisement happens, means what is the behavior of selecting the best path, right? So like distance vector, if any protocol which is type of distance vector, uh, that means the best path selection happens basically based on the hop count, right? And when it is link state, the best path selection happens based on the calculated metric of the link. And when we say the hybrid is basically the combination of distance vector and link state both, right? Again, not going to get into too much. And then these are the protocols we have. So like RIP, IGRP in distance vector, OSPF and ISIS in link state, and EIGRP in hybrid. So RIP, IGRP, OSPF, ISIS, and EIGRP. So these are the actual protocols. Yeah, RIP is distance vector, IGRP is distance vector, OSPF and ISIS link state protocol, and EIGRP is hybrid protocol or hybrid, right? And now we cannot forget the EGP as well. So EGP is something called BGP, yeah, border gateway protocol. And BGP has got basically two, types of BGP, I would say, the IBGP and EBGP. IBGP and EBGP. So we'll talk about the BGP later. What is IBGP? What is EBGP? We'll talk about that. But as of now, I believe it's quite clear for everyone. This is quite important basically. Okay, when we talk about the routing, IP routed, IPv4, just to make it kind of look good, I would say I'm sorry, I'm just focusing more on this design as in the diagram. IPv6. No. So IP routed, either it would be IPv4 or IPv6. Yep. So that's something about the routing. Hope this is pretty much clear. Now, what we are going to discuss is how exactly the routing happens. How exactly the routing happens. Okay, so for that I have to design a network. Let me just pause the recording. All right, perfect. So this basically topology, in this topology, what we're going to discuss is how exactly the packet flow happens, right? So as you guys know, R1, R2, R3, R1 is connected to R2 using this particular subnet, 1.1.2 here and .1.2. And then we are having 192.168.1.0 network /24, where .1 on this interface, .2, .3, MAC address A, B, and then C, D, E, and further. These are the MAC addresses, and these are the IP addresses configured, right? Now, what I want to discuss here from the PC1 perspective, you being a network engineer, when you initiate a ping, right, from PC1 to PC, let's say 5, right? So what you use basically is ping and let's say 192.168 and 3.2, right? And hit enter. Once you hit enter, what exactly happens over here in PC1? You got my point, right? What exactly happens over here in PC1? Anyone in this group, basically.
It um it looks for the path to the destination.
It looks for the destination.
Yeah,
Okay,
where
so
the packet's gonna be sent.
the destination is 3.2. Yeah.
Yeah,
Okay,
3.2.
3.2. Perfect. So what you're saying is the PC1 is going to look for 3.2.
Yeah.
What else? From the processor, from the processor level as well. Yeah, so not going to make a note of each and everything, but what I would say is the moment you enter here, what would happen is, sorry, what would happen here is this PC, right, at the processor level, going to understand or recognize this command, what this command is. Okay, ping. Now PC, the processor knows that, okay, this basically the command ping means it's kind of instruction for me to send what? ICMP echo request, right? So this PC is going to now, this PC knows, PC1, that, okay, I have to send an echo request. Now, to what address? This is something the numeric value. PC doesn't understand the numeric. It is going to convert this into binary, right? And then going to see whether this 3.2 is in my network or it is outside of the network, right? So obviously it is going to compare this binary number after conversion to binary number, right? It will compare with its own IP address binary number, what it has got configured. Now it sees that the binary numbers are different. That means they have to send, PC1 has to send the request to outside, right? Now the PC1 has determined that, okay, this is not in my network, this is somewhere else. So in order to reach or in order to send this echo request, I have to send it to my gateway, my default gateway, and that's where you would configure default gateway. If you don't configure default gateway, PC1 is going to drop it here itself, saying that, okay, I don't have default gateway, I don't have the default gateway to reach, hence I'm dropping it. So let's say the default gateway here we have configured .1 as predefined. So PC1 knows that, okay, fine. Uh, in order to send outside, I have to send this basically ICMP echo request to where? to my default gateway, which is .1. Okay, now before sending it, right, if we talk about the OSI model, right, so ping basically works where? Ping works at the network layer,
Network layer.
right? And what's the full form of ping? Packet Internet Grouper. So basically at network 3, what it would do is, when we talk about the OSI model, you guys might have gone through it. When we talk about the OSI model, this PC1 has to use that reference, like all the all the layers has to be used. So anyways, top layer application, we have opened already the command prompt resides in the application, isn't it? So we are already up in application layer. Session is something already created, right? Presentation is something encrypted. And when it comes to the transport layer, since ping basically works at the network layer, so the transport layer here as of now won't come in a picture, right? When we open the layer 3 header, in this layer 3 header, what all going to be there, right? We will have the IP header, you will have the IP version, you will have the source IP, destination IP, you will have the TTL value, you will have IP protocol number, most importantly you will have the offset bit and etc, subnet, and then the subnet mask and all, isn't it? So this basically, from the layer 3 perspective, this is going to say that, okay, for me the source is what, the source IP is going to be 1.2, right? Let me just put it like this. Yeah, 1.2. Destination IP is going to be 3.2. Yeah, apart from TTL value and all that would be there. When it comes to the layer 2, it is going to say, okay, source MAC, which is my MAC, is what, A. And what about destination MAC?
L.
So the destination MAC,
L.
is someone asking question, or if you can
Sorry, I got a question. Like if the IP is found in their own network, so don't they have to go to the gateway after
it
that?
won't, no. The gateway would be used only when you are sending it outside of the network.
Okay, thank you.
Okay, so since PC1, in your question, PC1 wants to communicate with PC2, PC1 is going to convert it to binary. It knows that, okay, both the binary are in the same network, means I don't have to use the gateway, I can send the request directly. But again, the flow is going to be almost pretty much same. Okay,
Thank you.
now coming to the destination MAC address, what this destination IP anyways, since we have entered it, PC1 knows that, okay, destination IP I have to reach 3.2, right? The source MAC and source IP is something its own information of PC1 about the destination MAC. The destination MAC is something, obviously, when it comes to the first time communication, right? PC1 would not be knowing what is the MAC address of .1. So what it would do, it would use ARP, Address Resolution Protocol, isn't it? And using that ARP, it will send an ARP request, right, to .1.
Sorry, can I ask? So will it be SM or the DM that will send an ARC? No, SM no. So it will be DM that will be
The
asking the
destination
ARC
MAC address,
request.
right? Because
Okay.
we want to learn the destination MAC.
Yeah.
I want to learn what is the MAC address of 192.168.1.1. Wherever it is configured, I don't know. But ultimately what I'm going to do, I'm going to send an ARP request. How does that ARP request looks like? Okay, or the look like? Okay, let me, anyways, destination MAC, for just to complete this, I'm going to put destination MAC address. See here, I would explain why and how, but as of now, how the ARP looks like, right? So now the ARP would be, okay, ARP, and in this ARP, you would have source IP, which would be again 1.2. Destination IP is going to be 1.1 because I want to know the MAC address of what IP?
3.2. Destination finally we want to know, but
Yeah, I mean, thanks for reminding me because I was almost kind of, about to skip that. Yeah, let me just do this. What would be the destination? So PC1 wants to learn the MAC address, right? And here the destination is 3.2, isn't it?
yes, yeah.
Yeah.
So, and the PC1 doesn't know what is the MAC address of 3.2, isn't it?
Yep.
Hmm.
So what would be, so PC1 is trying to know the MAC address of what IP? Answer.
You want to know the destination 3.2, but the next maybe the device routing device first it has to know 1.1.
Okay, so what you're saying is the MAC address, the PC1 would try to know or learn the MAC address of 1.1.
Yes, first yes, that's the next.
Why not 3.2?
Because it's a default gateway, and through that only it has to go into learn the route to reach 3.2 because it's outside of the network.
Anyone else?
I think because ARC broadcast as well. So if it will send 2.1, I think it will be broadcasted to all.
Yeah, but initially the broadcast should go switch one. It's which are the routing the default gateway connected through the switch. It will broadcast, and maybe that's why it has to know the first router 1.1 MAC address.
Okay, so here, just remember one thing, ARP request never crosses the network. The ARP request,
Okay.
resides within a network. ARP request works within a network. Means if the PC1 is trying to send the, ARP, learn the, sorry, uh, if the PC1 is trying to learn the MAC address of, or wants to learn the MAC address of 3.2, it won't be possible. The reason being because if PC1 knows that the 3.2 is in different network, and my ARP request cannot be reached to 3.2,
Okay.
right? So what I'm trying to say here is ARP request never crosses the or never goes out of the network. It would be within the, network itself, one
Okay.
network, right? So learning the MAC address of 3.2 is not possible. Why? Because 3.2 is somewhere in different network. Yeah.
Yep.
So what PC1 is going to do, it is going to learn the MAC address of its own gateway, because the gateway is providing the PC1 as a kind of, the proxy, I would say, or saying that, okay, PC1 can communicate rest of the network outside through me. So the gateway is something going to, serve. So how this ARP request would look like now, say ARP, and then source IP is going to be 1.2, destination IP going to be 1.1 because the PC1 wants to learn the MAC address of 1.1, and the source MAC, obviously it is going to say I am MAC address A, and when it comes to the destination MAC, it is going to be what? FF, FF. How many times it is? 1, 2, 3, 4, 5, and one more.
It's broadcast.
Yeah,
Yeah, broadcast IP, right? Yeah.
broadcast IP, not IP.
Oh, no. Okay.
Layer 2 broadcast. This
Layer
is
to
something,
broadcast.
this
Yeah.
address is called as a layer 2 broadcast address. Yeah, you would have layer 3 broadcast address as in 255.255.255.255. Clear?
Yes.
So
Yep.
this basically, when the device sees, which device, let's say when this ARP now message, when ARP request goes through PC1, switch 1, I'm not talking about switch 1 here because switch 1 is acting just like a transparent bridge, just like a layer 2 switch sending the request outside or wherever it is required, or maybe doing broadcast initially. So finally, when R1 receives that ARP request, right? Just remember in this, guys, I'm just trying, I'm basically stretching this topic, but would be definitely useful for you guys. Okay, when PC1 sends the broadcast, switch 1 is going to send a broadcast to everyone, all connected ports, means that the broadcast would be sent over hold on, what happened? Oh, would be here and would be here, where that is gone. Right? So anyways, so when PC2 receives it, at the end, it is the signal that PC2 is receiving. PC2 cannot ignore it. It would open it. It knows now that, okay, someone is trying to learn the MAC address, and MAC address A is trying to learn the MAC address of 1.1. But since I am 1.3, I don't have to do with this at all. PC2 is going to drop it. When R1 receives it, what it would do, it would reply of that ARP request, saying ARP message, saying, okay, uh, my source IP is now, since R1 is replying, it would be like source IP is going to be 1.1. Not going to write everything. Destination IP is going to be 1.2. Source MAC is going to be C, and destination MAC is going to be A. Right? This is what it is going to be in ARP reply when R1 replies. Finally, PC1 knows that, okay, what is the MAC address of 1.1? MAC address C. Apart from PC1, PC2, switch is also very intelligent device. Switch is also going to learn those MAC address. So if switch one is listening MAC address A on this port, it is going to keep it in CAM table. Same way when C is replying, switch is going to keep this C MAC address on this interface and going to keep it in CAM table. That's something part of switching we'll discuss. But anyways, ARP done. Now PC1 knows what is the MAC address of 1.1.
It's
That's correct.
broadcast the connected devices, and it got reply from the R1.
That's correct.
Okay.
Yeah.
So that
Go ahead.
that record, the op record should be held by the PC. Even switch also we can find, right? Once it's resolved, through there also we can find, and we can. But in PC, yeah, we checked, it's possible we can get that op request, maybe address for MAC and IP. But even switch also, right? But originally the old that table of that op.
Yeah, the switch one also is going to learn all the MAC addresses connected on the interfaces. And for that, you can verify using show MAC address table.
Yeah.
On the
So,
switch.
but the op table should be is even from the switch we can get the details, right?
ARP table, you are not going to find it out because none of the IP addresses are residing here.
Okay.
You would
Okay.
only see the MAC addresses, connected MAC
Okay.
addresses.
Okay. Then maybe in R1 and PC1 I can see
Correct.
that op details, I think, right?
Yes.
Okay. Okay. Thank you.
Yep. Hope it is clear. So after knowing the MAC address of default gateway, now PC1 is going to send what? Let's back to the business now. The PC1 is going to send it was about to send. It was about to send the echo
3 dot.
request,
Okay. Okay.
right? Now when echo request is sent, it would be sent using these details, right? Now the packet would go to the switch. Through the switch, it would go to the R1. Yeah. Now what R1 is going to do, it is going to open that packet. Okay, R1 is going to open a packet, layer 3 header when we say packet, and going to check source IP is okay, 1.1, 1.2, destination IP is 3.2, right? So apart from the other details, if you talk about the TTL value something, whatever TTL value is come, that basically depends on what end device that you are using, Linux or the Windows based, TTL will get changed, accordingly. But when R1 receives, it would open layer 3 header and going to check all those parameters. Okay, so R1 has to send it to 3.2. Okay, now the question is, R1 is, does R1 know where is 3.2? And in order to verify that, R1 is going to check RIB table, routing information base, or you can say the IP routing table, right? So R1, if it finds the 3.2 or maybe 3.0 network in its routing table, it is going to forward it to the respective next hop. But if it doesn't find it, right, maybe you haven't done the routing yet, or you missed it out, or some wrong configuration, whatever, what would happen here is R1 is going to drop the packet because R1 further doesn't know how to reach out this guy 3.2. Okay, so R1 is going to drop the packet. Okay, R1 has dropped it. Now how the PC1 would get to know what happened to my packet or echo request? So whenever we use ping, the protocol called ICMP, yeah, ICMP is going to be used here along with the ping. What is ICMP? Internet Control Message Protocol, and it is going to, you know, generate the packet status. I mean, the ICMP, the status of either the ICMP echo request or echo reply. ICMP tells the originator what exactly happened to that packet. So ICMP is going to generate a message over here in PC1 saying that the reply from .1 over here, reply from .1 destination host, this destination host is unreachable. So that something means that the issue is the issue is basically while packet is going outside, means the issue is outgoing direction. So again, being a network engineer, you guys just make a note whenever you see the destination host unreachable, that means there is an issue while sending the packet. Now it could be the issue, to the PC1 configuration itself. It could be the issue with the R1 or maybe R2, anywhere. But since we are receiving the reply from .1, that means R1 doesn't know how to forward it, right? So that's again another kind of a point where you can start troubleshooting by looking at the output, saying okay, destination host unreachable .1, that means the issue is in R1. Let me just go ahead, log in R1 and check, rather log into the router 2 and R3 and checking, and trying troubleshoot. Yeah, so finally R1 has dropped it, the packet is gone, but now we want to fix it, isn't it? So after looking at the output, we would log in R1, and let's say we fix up the routing issue. Maybe the static entry we make it here, saying in R1, okay, to reach 3.0 network, to reach this network, send the packet to your next hop IP, this guy over here, .2. Over here it is .2. I haven't noted, maybe the .1. and dot 1, 23.1 and 23.2, or maybe 3, right? So when R1 finds the entry in its routing table, it is going to generate a packet again, or the same packet would be sent there. So from R1 perspective, the when R1 is sending this source IP, that I'm gonna ask you guys, source MAC, these details, destination MAC. Yeah, what would be the source IP when R1 is, sending it? Anyone? So the packet is with R1 and R1
So-
wants to process it.
12.1.
12.1.
12.1. No. So just remember one thing. Your source IP and destination IP
Won't get changed, sorry.
won't change unless and until you are using some natting and all that,
Yeah, that's correct.
right?
Yeah.
So the source IP and destination IP would never change. Source IP is going to be still 1.2. Destination IP is going to be 3.2. But yes, in case if you are using NAT in R1, saying that this is a private IP, cannot go outside, I have an IP address who would be getting translated to, that IP would be used, by the way,
Okay.
right? So just, add that scenario as well in this. So in case whatever, let's say this is the 12.1 is the public IP that I have, and I have configured R1 as a NAT. I have configured in R1 saying that whenever, let's say the port address translation, whenever the private IP address comes, drop it here and take the 12.1 and go outside. So in that case, obviously the source IP is going to be 12.1.
Okay.
Yeah. Okay. Now, what about the source MAC address? Is the same case with the MAC address as well, or will it get changed?
It's the same. Yeah.
Same. So just remember, MAC address is something, hop by hop or network by network, it would change, or the interface by interface, it would change. Okay. Just remember, there are two scenarios over here. If this is a serial link, since there is no MAC address on the serial link, right? Your MAC address layer 2 information won't be sent over WAN. You got my point, right? MAC address will never ever be sent over the MAC, over the WAN, if it is serial connection and all those.
Okay.
But in case if you have like, Ethernet connection towards the service provider, yeah, in that case, you would have the MAC address configured, or, in this interface. So in that case, you would be using source MAC as in D and destination MAC as in what? This next hop IP MAC address, which is E. Again, R1 doesn't know what is the MAC address of dot 2. R1 has to send an ARP request, ARP, to learn what is the MAC address of dot 2. Why? Because this is something
Different.
LAN interface, just remember. That's why if it is serial, let's say, for example, if it is serial connection, there won't be any MAC address over here. There won't be any MAC address over here. In that case, this source MAC and destination MAC would be not added to it. Only this much information would be sent if it is serial link, other than the, LAN interface. Clear?
Yeah. So the reason it's the source MAC, it took because of the it not took
Because
the
R1 is sending the packet further on the LAN interface, and LAN interface has got the MAC address.
Okay, you told it's MAC address based on the interface where it's sending that MAC address we have to give, right?
Yeah.
That's what. Okay. Okay.
So if it is a serial interface, on serial interface, there is no MAC address,
Yep.
correct?
Correct.
Because there we would be using SDLC or the TPP protocol. So there won't be any MAC address. And that time, in that scenario, there won't be any MAC address sent here, added here. But since this is Ethernet environment, there would be source MAC D and destination MAC, E.
Okay. Yeah.
Clear?
Yeah, clear.
Okay. Now, along with when it is sending it over here on this interface, just remember in layer 3, we have the TTL value as well. TTL value will be reduced by 1. So if R1 has received, let's say the TTL value is in 253, for example, when it is sending it out of this interface, the TTL value would be reduced to reduced by 1, and it would be 252. So means when R2 receives it, it would receive the 252 TTL value. Okay. Now when R2 receives this packet, okay, which one? This one. R2 is going to do the same thing what R1 has done. It is going to open layer 3 header, going to check who is source IP, destination IP, right? Okay, source IP is 1.2, destination IP is 3.2. R2 is going to look at the routing table. If it finds the information in its routing table, going to forward it. If it doesn't find, it'll drop it there. Again, ICMP would generate a message here saying the reply from dot to maybe. Just remember, by the way, every time when the packets are getting unreachable, the reply you would see the reply dot one itself. But the troubleshoot is something you have to approach, troubleshooting first R1 and then troubleshooting R2 and R3 like this. Yeah.
Okay.
Cool. As well as it would open it would also check the source MAC and destination MAC because it has received it on LAN interface, and again R2 is going to send it on the LAN interface. So this particular part would remain the same, but this part would get changed.
ING.
Yeah. So source MAC would be I and then destination MAC would be J. Okay. Finally, R3 has received it. R3 is also going to do the same thing. Going to open layer 3. R2 is going to reduce the TTL by 1. So it will become 251. R3 has received the TTL value, not 251.
So
Yeah.
the time to live, right? You are mentioning.
Correct.
So each router it reaches, it will drop one. That's what you say.
By 1, it would be dropped.
So why is the TTL value dropping?
Well, first of all, you have to understand what is TTL value. Okay, what it does, right? So I would say TTL is layer 3 mechanism, or you can say layer 3 feature that used to prevent layer 3 loop. So in case if some information keeps on moving across the WAN, right? So when the router finds TTL 0, that packet would be dropped.
Okay.
Yeah. Perfect. So R3 is going to open layer 3 header, going to check source IP, destination IP, since 3.2, 3.0 network is directly connected over here. R3 doesn't need routing for this, as in it doesn't have to learn from me anywhere because it knows that, okay, this is something directly connected to me, right? And would check the source MAC and destination MAC. Now R3 going to process this packet saying source IP, destination IP, source MAC, and destination MAC. Yeah, the source IP is going to be what? The same, 1.2, 3.2. Source MAC is going to be now K. Destination MAC, if it doesn't know, it is going to send ARP. With the ARP, it is going to learn what is the MAC address of dot two. Dot two is going to reply with its own MAC address saying destination MAC is L. And finally, R3 would send that ICMP echo request to this interface. Now, just remember, there would be IP protocol number as well. Okay, whether you are sending ICMP echo request, for the ICMP echo request, there are codes basically for the ICMP request. I mean, you can browse internet and just, you know, have more information about those codes, whether it is type of 8 or whether it is 1 or 0. That's something you know, browse it in internet. You would have a whole lot of idea about it.
What's that? ICMP.
ICMP codes. Yeah. Finally, PC5 receives this packet as an echo request. Since PC5 receives the echo request, PC5 has to send what? Echo reply.
Okay.
So
That's
any device that receives the echo request, it knows that I have to send echo reply, isn't it? That's the beauty of ping. Ping is something, you know, you would check the connectivity across the network, not only one way, but both the direction, right? So PC1 has sent echo request, PC5 has received echo request. Now, just to confirm that, yes, I have received your echo request, PC5 would send echo reply. When PC5 sends echo reply, it would have again the same process what PC1 has done. Yeah, it would check. All right, now who is source MAC? The source MAC is so who is going to be the source IP? Now this time the source IP is who? 3.2. Source or the destination IP 1.2. Source MAC, its own MAC address L. Destination MAC, it is going to check with its gateway using R and K. Yeah, and PC5 is going to send it to R3. Now R3, when it opens the layer 3, it is going to check the who is destination IP. Now the destination IP is 1.2. Does R3 know where is 1.2? Two scenarios. Yes, it knows. Second, it doesn't know. In case if it doesn't know, maybe routing is not done for particular this subnet, R3 is going to drop the packet. Where? It is going to drop the packet here because it is receiving it from PC5 on this interface. It is going to drop it. Yeah, so once it drops it, again ICMP would all the way go and generate the message here. What?
Destination unreachable.
No. Request
timeout.
timeout. Yeah, and as soon as you see the request timeout message in your command prompt, that means the issue is when the packet is coming towards me, means inbound direction, now not the outbound direction. And that's where you would start troubleshooting not R1, but this time you would log into R3 and check the, you know, IP reachability, check the IP routing, R3, then R2, then R1, like this. Yeah, clear? Okay, another scenario, if it knows, okay, how to reach 1.2, well and good, it is going to send the packet to next hop IP using same method. R2 is going to open layer 3 and send it to R1, and finally R1 is going to send it to PC1. PC1 receives echo reply happily, and you being a network engineer quite happy, saying that we have the reachability, the issue got fixed. Yep. So this is why I have taken so much time to explain this. Trust me, going to be very, very important. most of the interview questions, they would ask from this diagram. That is how they'll check your knowledge, the concept, whether you have a proper concept clear or not. Okay, so my suggestion would be explain yourself once again offline. Okay, that is how it happens. Then this would happen. You can, bring some more other scenarios as well. What if we have firewall? What if we have, NAT configured, and come up, maybe, come up with the questions. But that's something very important. The whole routing is dependent on particular this flow. Yeah.
What's RIB once again? Routing. What's the full form of it?
Routing
RIB.
information base. All right. So hope everyone is back.
Yes.
Cool. So after routing flow, right, what we have discussed in routing flow, basically how the packet takes, goes through one by one, how basically ARP works as well, end-to-end process, isn't it? So now next topic is going to be the EIGRP protocol. So we'll now talk about EIGRP protocol itself. As you see here, EIGRP comes under the hybrid, right? So that means EIGRP is a protocol that has both the characteristics, distance vector as well as the link state, right? Guys, this is again an interview question. They ask what all are the, feature of distance vector in EIGRP and the feature of link state in EIGRP. So that might be, you guys offline just do some research into it. What would be the feature of distance vector that we have in EIGRP, and what would be the feature that we have in links off link state. Apart from that, why EIGRP is called as an enhanced interior gateway routing protocol? Because IGRP, you see something over here as well. We have IGRP here, right? So they ask why EIGRP is enhanced interior. So obviously, EIGRP is something the enhanced of IGRP, right? So EIGRP has been introduced by taken from IGRP. So most of the characteristics of IGRP is there in EIGRP. That's the reason actually why it is, combination of distance vector and link state. Apart from that, it has got other features as well, like of the link state. Few of them would be like in distance vector, we have only one, that is routing table, one table, routing table. Uh, but here in, link state, we have like routing table, we have neighbor table as well as the topology table. Yeah. Apart from other features as well, other characteristics that probably you would find it. I don't want to discuss it right now. Let's not make it more lengthy. But yeah, I mean that's quite often oftenly asked this question basically about EIGRP. So while going through the training, while going through the EIGRP protocol, we'll keep on discussing what are the interview questions as well that they ask, and accordingly you can be prepared. All right, perfect. All right. So in EIGRP, if we discuss, let's start from the theory, kind of a a revision of what we have studied in CCNA. So what's basically EIGRP? to talk about the characteristics. Enhanced interior gateway routing protocol, isn't it? I would say, first of all, it is an IGP protocol. Yeah. That means EIGRP works under the IGP, right? And then a type of, it is a type of hybrid. And what is hybrid? Where the combination of distance vector and link state. Apart from, I mean, you guys can also mention the points, what you remember. Go ahead, please. Yeah, anyone? What is EIGRP? Any characteristic of EIGRP that you remember?
Yes. It's a classless. routing protocol.
Yeah, so EIGRP supports classless as well. That's true. Yeah, so it supports classless routing. Yeah, what does that mean? That means supports CIDR and DLSM.
Yes. Yeah.
What else?
Is a Cisco proprietary?
It's open in standard.
Oh, now it's changed. Okay.
Yep. CIGRP is open standard.
The op count is 255. Maximum like RIP having 16, it's having 255. Op count.
By default, it supports
100.
Hop count 100, but can be
Maximum.
increased to 255. What else?
It uses multicast and unicast instead of broadcast. Sometimes that helps.
EIGRP supports unicast as well as multicast. Yeah, go ahead. How about the metric? What metric EIGRP supports? Metric, where the metric supports as in K1. K1 is called what?
Yeah. Bandwidth and delay.
K2, that's basically in sequence. Just remember the sequence, which is called load. K3,
MTU,
which is delay. No, this is basically in sequence. So whenever you are answering this question in interview and all, you have to tell them in sequence, because K1 is what? Bandwidth. You cannot say K1 is load. You cannot say K2 is delay, something like that.
Okay.
What about K4?
Then it should be a MTU or reliability.
We have reliability and MTU.
MTU.
Yeah. So yeah, reliability. And K5,
is that
which is MTU.
Yeah, that's it.
So just remember, these are the 5 metrics that EIGRP supports. Okay, supports metric 5 matrix K1, K2, K3, K4, K5, out of which one is used?
Bandwidth and delay.
K1 and K3 are turned on. That means the value of K1 was going to be 1, which is bandwidth, right? And the value of K2 is going to be 0. The value of K3 is going to be again 1.
1.
Yeah. And the value of K4 is going to be 0. And the value of K5 as well is going to be
0.
0. Yeah, that's the matrix. Okay, question. Why do we use matrix here? The simple matrix is used for selecting the best path. So any dynamic protocol, any routing protocol, they use matrix to select the best path out of multiple paths. Okay.
Yeah.
Next one is AD. How about the AD, administrative distance? Yeah.
It's a 90 for internal and external 170.
Yeah, so that's correct. So what is AD? AD is basically, again, AD is again a numeric value, right? Which tells you what protocol is, what is the trust of that protocol. That's something between 0 to 55, where the least AD is going to have more trust, right? What about the matrix? Matrix is going to be a criteria to select the best path. So you have so many matrix, right? Out of those matrix, some of the matrix would be used by some of the protocols. So here in EIGRP, the AD is what? 90, right? EIGRP AD is 90. For internal prefixes, and for external, it is 170. What is the AD of connected interfaces? The connected interface AD is going to be 0.
0.
Yeah. The static and default is going to be 1. So the connected is more trustworthy. And then you have EIGRP, then you have OSPF, then you have RAPE, and then so. BGP.
Sorry, can I ask something?
Go ahead, please.
So what's the difference between like this internal and external EIGRP?
EIGRP, okay. That's something we'll discuss, but
Okay.
as of now, internal is something only EIGRP originated routes.
Okay.
External is something the routes which are coming from outside, different protocol, redistributed routes, and all.
Okay. We'll discuss them later. So
Yeah.
Okay.
What else in EIGRP, guys? So EIGRP supports what? It supports AS, autonomous system number.
Yeah.
Right?
Yes.
And what is the role of AS in EIGRP? It basically is to segregate the routing table. Right? So EIGRP basically nothing has to do with the AS number, what we have discussed, like interdomain routing and all that. Here, yeah, it does support AS number. We call it as an AS number, but just to segregate the routing table. Okay. Next, what else?
Segregate the requirement and to
So
do that.
maybe in one router you are running two AS number.
Okay.
Okay, EIGRP AS number 100 and EIGRP AS number 200. So the routing prefixes would be, in 100 separately, and 200 would be, maintained separately.
Okay.
All right. Apart from the other, points that what we have discussed in EIGRP, I would say automatic neighbor discovery. Yeah,
Yeah. Yes.
automatic neighbor discovery. What does that mean? That means neighbors are the neighbors are discovered in EIGRP automatically. How? Right? So it's
Send
basically by sending
hello packet every
hello
5 seconds.
packet in every 5 seconds, and hold is going to be 15 seconds. Yeah. So
Okay.
that means, why this is not going? That means the EIGRP basically, as soon as you advertise the network, EIGRP is going to start sending uh, hello packet in every 5 seconds on that interface. Yeah, EIGRP is going to start send hello packet on that interface in every 5 seconds. So we'll be talking about the packet types as well. EIGRP packet types. What else? Any other point? Okay, now the question is, what address that hello packet would be sent to? Yeah, what address that EIGRP hello packets would be sent to?
Um.
So that hello packet would be sent to the multicast address.
Yes. Yeah.
Multicast address 224.0.0.10.
10.
Yeah.
Yep. Yeah.
All right. So that's something we'll talk about more when we do the lab. How about the EIGRP? Which layer basically EIGRP works?
Layer 3.
Layer 3.
Network layer.
Network layer. And how?
It's work on IP based the
In that
routing.
case, what about RIP?
Yes, that also same.
What about BGP?
Yeah. Same.
No. So
No.
I
Yeah.
mean, it works in. I mean, especially EIGRP works in layer 3. That's correct. But why it works? Because it works in layer 3. Why? Because I'm not gonna. Okay. Because it uses protocol number. Just remember, protocol number, not the port number, like TCP port number, UDP port number, and all that. Not protocol number, IP protocol. We have a field IP protocol in layer 3 header, if you have noticed ever. Right? So here, EIGRP uses protocol number 88.
Okay.
Okay, so if you block this 88 port number, maybe using the access list, the hello will never be sent. The EIGRP will never ever found the neighborship.
Then even after that, there is no routing information. Information also won't share, right?
Exactly. Why? Because when it sends the multicast, okay, hello multicast address, it says that I'm the protocol number 88, means I am EIGRP. I am, I am working in layer 3 and my protocol number is 88. Yeah.
But actually, it's a IP protocol, right? Not TCP UDP, right?
Yeah, this is IP protocol. Yeah, that's what I said. It uses
Okay.
IP protocol number.
So it's
Yeah.
having same like RIP and as well as OSPF, the IP protocol
No,
number.
in RIP we don't have any IP protocol number. Yeah, OSPF we do have. In fact, the BGP also we don't have IP protocol number. So that means CIGRP and OSPF both work at layer 3.
Okay.
So, you just said, Ravi, that layer 3 header has a protocol number field. So do they have by default this protocol number 88
In EIGRP, in case EIGRP.
in case of, so in case of EIGRP, then only they'll have protocol number 88,
Yeah,
not
that's correct.
otherwise. Okay, so not by
Say,
default.
for example, if it is OSPF, the port number, the protocol number would be 89.
Okay.
So the field, the in a header, the field won't be there for BGP and RIP, right? So only for
Yeah,
BGP. Okay.
yeah. I mean, the field would be there, but it would be like nothing.
Mhm.
It won't be present, the number. Okay. Apart from about those points, what else? So basically, not
Load.
going to discuss everything as in theoretical wise today itself. I guess as in the introduction class today, pretty much I think enough. So maybe a couple of points that we would discuss, and then we'll move to the lab tomorrow.
Okay. And load balancing also, like equal cost and
All right.
unequal cost.
So it does support. So it supports 4 or 6 equal path. 4 equal path load balancing
And even
and
unequal also.
16 unequal path load balancing. That's something we would discuss what it is.
Okay. Maybe the one more, the algorithm is like diffusion update algorithm, something, right? For EHR.
Yeah, that's correct. Yeah. Okay. Right. So what points we are discussing where we don't have to get into the lab anyways, but those points again we are going to discuss through the lab as well when we do the lab. So that's not an issue. Sixteen unequal path load balancing. Hello, I don't know what happened exactly. All right, so let's do one thing. Whatever we have discussed today, let's keep it for today only. Okay, and the remaining topics, remaining points of EIGRP as well as getting into the lab, we would do it tomorrow. Yeah. So that's it
Okay.
for today. Yep.
Okay, and we'll